Hi there, folks. In this lesson, we're going to look at the components of rational function graphs. All right. So we're going to kind of look at the simplest version of a rational function, get a feel for what it looks like, and then we're going to start identifying the pieces that are incorporated into the graph. All right. So today we're not going to do much graphing. We're going to start off with a really simple graph, and then we're going to learn about the pieces and then how to identify those pieces. And just like any other function, there are certain characteristics of the graph that we look for. Like linear functions, we know all about slope and how the slope works and how we use slope to graph these things. Here, we're going to look at things that are a little bit more abstract, things that you don't really have much of a concept for, asymptotes and holes in the graph. And it all kind of goes back to what we've been doing in terms of finding domain restrictions. So we'll kind of see what that looks like as we move forward. So let's start off with a really simple graph, y equals 1 over x. And just like anything else we've ever graphed, anytime we don't know how to graph something, we start with this simple version and we do an xy chart. So here we go. For our xy chart, typically we start off with these values, right? -2, -1, 0, 1, and 2. And I very suspiciously left a little bit of space at the beginning because maybe this won't be enough, and we'll see. But if I plug like a -2 in there, 1 divided by -2 is just a -1/2. If I plug a -1 in there, that's a -1. If I plug a 0 in there, that's impossible. I can't do that. That's undefined. Remember, that's one of our domain restrictions. And if we were kind of coming up with the domain, we would say, hey, it's this thing, but x can't equal 0 because that would make the denominator 0. All right, and that's something we're familiar with. It should make sense to us that 0 doesn't work. All right. If I plug a 1 in there, I get a 1. And if I plug a 2 in there, I get a 1/2. And so as I go to graph this thing, looks like this. Ready? -2, 1/2, or sorry, -1/2, -1, -1, and then 1, 1, and okay, looks kind of like gibberish at this point. And I get all kinds of stuff when students see this at first, and I ask them, hey, what's the deal with this graph? What does it look like? You could guess all day long, and you're not going to figure it out. All right, so let me give you some wrong guesses here. Students go, oh, it's clearly a set of parallel lines. Oh, right. Yeah, parallel lines. Okay, well, but now it's not a function. It doesn't pass the vertical line test. Plus, how do I have a value here at 0? Remember, 0 is undefined. Here's the x value of 0. It says that I have a y value of 2. Here's an x value of 0. It says I have a y value of -1/2. So that's impossible. It can't be that. It's not a set of two separate lines. That doesn't make sense. Students will say things like, well, maybe it goes like this. It's like a zigzag, so it's got to come up here and connect these, and then it does that. Well, again, we're still violating this right here. X can't equal 0. Well, here's a point at 0. That shouldn't exist because x can't equal 0. All right. So really, we can't tell what this thing looks like just from those values. All right. And students will try this. They'll say, okay, let's expand our thinking a little bit. Let's tack some 3's on. So now I get a -1/3 and a +1/3. All right. And that's great. That gives us a little bit more information. We got this thing here and we got this thing here. So now students go, oh, it looks kind of like an exponential function. All right. We're still going to be wrong, but it's a good try. They say, oh, looks like it's hugging this guy. And then it's going to be a curve that goes like this, right? Like an exponential function. And then this is going to be like a separate exponential function, okay? And again, that's still wrong, but you're a lot closer. The graph does kind of look like this, but we're still violating that x can't equal 0 thing, all right? And so the thing that makes this tricky is to get a better picture of this with just an xy chart, I need to include some fractions. See, there's something funny going on right here. Like when you look at where x equals 0 along this line or along the y-axis, okay? All the ordered pairs on that line have an x value of 0. Something funny happens there, and I got to figure out what it is, okay? And you might be able to kind of start to think about this, and maybe you're figuring it out already. But let's plug in some values that get closer to that line. Values like this, if I expand the thinking on my xy chart a little bit, and maybe I try something like a -1/2. Or maybe like a -1/4, or maybe a +1/2, or a +1/4. Start plugging in some fractions to bring me closer to the x value of 0. And see, if I plug a -1/2 in, 1 divided by a -1/2 is a -2. Remember, dividing by a fraction is the same as multiplying by the reciprocal. 1 divided by a -1/4 is a -4. 1 divided by a +1/2 is a +2. 1 divided by 1/4 is a +4. And so now I get some more values here. -1/2, -2. -1/4, negative 4, it's right here, going the other way. See, now I'm getting some values that kind of give me a better idea. And so we were close the last time. It does kind of look like those exponential things. And we were right in that it's going to hug this line right here. But the thing we missed is that it's also going to hug this line over here. And so here, we're going to hug this line over here, but it's also going to hug this line up here. All right, this is a rational function. And what happens is we kind of get the situation we got with exponential functions where it's hugging that line but never touching it. See, like when you look at this guy, it's never ever going to touch this line right here. It's going to get closer and closer to it but never touch it. But the green line that I drew, this one up here, it's also never going to touch that line. It's going to get closer and closer and never touch it. And the idea here is we're starting to see these things that are called asymptotes, okay? Asymptotes describe end behavior. Think back to polynomial functions. End behavior is just what the function is doing on each end. And when we looked at exponential functions, we had an asymptote, but now we have two asymptotes. We have a vertical asymptote and a horizontal asymptote. We have two lines that this thing is approaching as it goes to forever. Okay, and so that's the idea we want to look at today. We want to look at these different elements, the different components like asymptotes, and figure out what they are and where they come from. Okay, and then we'll get into graphing some of these more complicated ones. All right, so let's talk about a vertical asymptote. Vertical asymptote is a vertical line that the graph approaches as y goes to plus or minus infinity. In other words, again, going to plus or minus infinity, that is end behavior. We already know that. We're describing end behavior. It's what it's doing on each end. Okay, so a vertical asymptote is describing the end behavior as we go up and down, essentially. All right. So these are found where we have non-removable restrictions, okay? And when you think about restrictions, we've been finding restrictions. Those are the things where you say x can't equal this or x can't equal this. It's the things that make the denominator 0. When we talk about a non-removable restriction, basically we find the restriction, but it gets canceled out as we simplify. That's a removable restriction. A non-removable restriction is the one that doesn't get canceled out. Okay, so when we think about the process of simplifying, we always found the restrictions first and then simplified. Well, here a non-removable restriction is the one that doesn't get canceled out. A hole in the graph is a point, and we didn't have one of these in the previous example, for which the function doesn't exist. It's just an empty kind of blank spot. So when we see a hole in the graph, we graph it like an open dot. All right, so maybe I have a line and there's just a point missing or something like that. Okay, that's a hole in the graph. It's just an empty spot where the thing doesn't exist. This comes from the removable restriction. Again, removable restriction, it's the same thing we were just looking at. It's still the domain restrictions that we've been finding, all right? But as in the process of simplifying, if one of those restrictions kind of gets canceled out and doesn't seem to be there anymore, we call it a removable restriction. It's a hole in the graph, okay? So these look complicated, but they're actually very simple to find because you already know how to find them. Okay, we're going to find the domain restrictions the same way that we've been finding domain restrictions, but then we're going to simplify the same way that we've been simplifying, and it's just a matter of saying, okay, which thing canceled out and which thing didn't cancel out. The thing that didn't cancel out is the vertical asymptote. The thing that did cancel out is the hole in the graph. Okay, for example, if I look at something like this guy, so here, when it says DOM, I'm saying the domain here. So I'm looking for the domain. So in other words, x can't equal what? All right. Okay, so to find the domain of this, remember, I just set the denominator equal to 0. I say, hey, this guy, x squared minus 16, is not allowed to equal 0. So I factor this into x minus 4 and x plus 4. And so when I solve that, actually, I guess we could probably solve that in our heads at this point, right? We set each factor equal 0, so we get x can't equal a 4, and x can't equal a negative 4. See, those are my domain restrictions, all right? And basically, each of those domain restrictions, when we interpret that onto a graph, that x equals 4 is either going to be a vertical asymptote or a hole in the graph. The x equals negative 4 is either going to be a vertical asymptote or a hole in the graph. And the way we determine which one is which is we simplify this thing. So if I were to simplify this guy, again, I'm just going to simplify the fraction by factoring it. So we're going to reduce the fraction. So up here, I build a bridge, two numbers that multiply to a negative 24 but add to a negative 2. It's an x minus 6, and this is going to be an x plus 4. The denominator, we already know, factors into an x minus 4 and an x plus 4. And as I reduce the fraction, you can see the x plus 4's cancel. Again, this is the stuff we've been doing. So the simplified version of this thing is this. And see, if I were to take that simplified version and say, okay, let's ignore the first half of the problem and just look at the simplified version. If I asked you, what's the domain restriction of just this thing right here? Like, what can't x be? You would say, well, the x minus 4, the denominator, can't equal 0. And if you solved that, you would get x can't equal 4. So you see that when we started the problem, we had 2 domain restrictions listed. But when you look at the simplified version, there's only 1 domain restriction. In other words, one of the domain restrictions has been removed, and the other domain restriction has not been removed. Okay? And so when you look at it, the x can't equal 4 is still there. That is a non-removable restriction. It didn't go away, which means x equals 4 is where my vertical asymptote is. And x equals 4 is the equation of a vertical line. That's where I'm going to see that dotted line that the function's going to get closer and closer to without touching. Okay? See, now the restriction that was removed, notice I had the restriction right here of x can't equal negative 4 listed, but when I look at the simplified version, I don't have that domain restriction anymore, okay? Which means that is a removable restriction. That's going to be my hole in the graph. And that's just the x value for the hole in the graph. I have to find the y value that goes with it. And I do that by plugging it into the simplified version. So right here, I'm going to plug that negative 4 into this guy. And I got to do it in the numerator and denominator. That's going to give me a negative 10 over a negative 8, which reduces to a positive 5 fourths, which, of course, we could write as, you could just do it as 1 1/4 or 1.25, whatever. But we want to write it as an ordered pair. A hole in the graph is a point. The vertical asymptote is a line. Okay? But again, it's all a matter of what's the domain restrictions. Now simplify. Which domain restriction is still there after I simplify, and which one is no longer there after I simplify. That determines whether it's vertical asymptote or hole in the graph. Let's look at another one. Let's do another one. Ready? So if I look at this guy, again, if I were to find the domain restrictions here, I would say the denominator can't equal 0, right? So now I build a bridge. 2 numbers that multiply to negative 12 and add to a negative 1 are a negative 4 and a positive 3. And if I set each of those equal to 0, I find out that x can't equal 4 and x can't equal a negative 3. So those are my domain restrictions, okay? To determine which of those domain restrictions are vertical asymptote and which one's a hole in the graph, or maybe they're both vertical asymptotes, or maybe they're both holes in the graph, is I just simplify the fraction. I say, okay, here I can factor a 4 out. Here I already factored this once. It was an x minus 4 and an x plus 3. And so what happens, we can see that these guys cancel. So the simplified version of this thing would be y equals, looks like a 4 over x plus 3. And so once again, if I were to just look at the simplified version and ask you for the domain restrictions again, you would say that x plus 3 can't equal 0. You would only give me the restriction of x can't equal a negative 3, right? And so the x can't equal negative 3 is still a restriction after I simplified, so it's a non-removable restriction. That's the vertical asymptote, okay? It's the restriction that's still here. It's still there. It's still a restriction after I simplify. It's a vertical asymptote. But notice, if I asked you for the domain restrictions of the simplified version, you wouldn't tell me x can't equal negative or x can't equal 4. That restriction has been removed, so that's my hole in the graph. So again, the 4 is still a restriction. We just don't see that restriction anymore after we simplify, okay? It's not there anymore after we simplify. It's still part of the problem, all right? But it represents a hole in the graph. And again, to find that, I'm just going to plug that into the simplified version here. And when I plug a 4 in, I get 4 over 7. So that's the ordered pair for the hole in the graph, okay? So it's doing the same thing that we did before, finding the domain restrictions and simplifying, But now we're interpreting those domain restrictions as either vertical asymptotes or a hole in the graph. And really, you just have to ask yourself, did the restriction get canceled out, or is it still there? Okay, so you have to kind of look at the restrictions before and after and compare them. The one that's still there is a vertical asymptote. The one that's gone is a hole in the graph. Okay, it's still a restriction, but it's a hole in the graph type of restriction. Okay, so let's talk about horizontal asymptotes, and we'll get into oblique asymptotes. But horizontal asymptotes are horizontal lines that the graph approaches as x goes to positive, plus or minus infinity. Again, that is n behavior, and it's looking at n behavior left and right this time. Okay, so n behavior left and right. This guy is also, oblique asymptotes, also n behavior left and right. When we talk about asymptotes, we are talking about n behavior. Vertical asymptotes describe end behavior up and down. Horizontal and oblique asymptotes describe the end behavior going left and right. Okay, that's it. All right. And because horizontal asymptotes and oblique or slant asymptotes are literally describing the same thing, notice they are the same definition. They are describing what the graph is as we approach, as x goes to plus or minus infinity. That means we'll have one or the other. You will never have a horizontal asymptote and an oblique asymptote. It will be one or the other. They describe the same thing, okay? And so we find these by comparing the degrees of the numerator and denominator, all right? This is the strangest thing in the world, but it comes from limits. As we plug zeros in for things, as we describe the limit of the function, this is kind of what it boils down to. And you'll get to this kind of stuff when you take pre-calc and calculus and that kind of stuff. All right, this will all become much more clear. For our purposes, we're just going to do a little bit of memorization here. All right, we're going to compare the degree of the numerator and denominator. All right. And depending on whether the numerator or denominator is bigger or whether they're the same, that'll tell us whether we have a horizontal or oblique asymptote, and it'll tell us how to find that horizontal or oblique asymptote. Okay. And so horizontal asymptotes are just when it's a horizontal line that we're approaching. Oblique asymptotes is when we have a diagonal line that we're approaching, a y equals mx plus b line. Okay. So here's what we do. And again, don't be intimidated by this, just a little bit of memorization. All right. So if we compare the numerators and denominators, if we look at their degrees, there are three scenarios that can happen. Either denominator has a bigger degree, the numerator has a bigger degree, or the degrees are the same. Okay? So if the denominator has a larger degree, we just say, oh, it's horizontal and it's y equals 0. Done. That's the one we should hope and pray for is every example that we're given. Oh, the denominator's bigger, y equals 0. All right? Done. All right? If the numerator and denominator are the same, this one is also horizontal. So if the degrees are the same, it's horizontal. But instead of just being y equals 0 or something like that, we actually divide the leading coefficients. We say y equals whatever number we get when we divide the leading coefficients. And again, that looks complicated, but it's not. It's easy, super easy. Okay? The only one that students tend to have a little bit of difficulty with because it involves a little bit more, and there's some things that we do here that seem strange to students. When the numerator is larger, so when this thing is top heavy, the top has a bigger degree, it's an oblique asymptote, so it's going to be y equals mx plus b, and we find the equation of y equals mx plus b by doing synthetic division. All right, so when the numerator is larger, we do synthetic division. But we don't keep all of what we get when we do synthetic division. We only keep the part that looks like y equals mx plus b. All right? And we essentially just get rid of anything that doesn't look like y equals mx plus b. Okay? Essentially the remainder from our division. For example, if I look at this guy, we want to decide if it's horizontal or oblique, and then we'll come up with the equation. So we look at the degrees. And remember, the degree is basically based on the size of the exponent. So when you look at this one, this guy has the numerator on this first one has a degree of 2 right here. All right. The denominator also has a degree of 2 right here. So when the degrees are the same, again, this is memorization. When the degrees are the same, I know that it's a horizontal asymptote. And what the directions told me a moment ago is when the degrees are the same, when it's horizontal, I just do y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So again, the leading coefficient is the number out front. Here it's a 3, and here it's a 1. So I do 3 divided by 1. So it's a horizontal asymptote at y equals 3. That's it. It's memorization. Students will always ask, they'll say, well, I don't understand how you got y equals 3 because I memorized what to do and I plugged the values in. It's easy math. It's just a matter of memorizing those 3 rules we just went over, okay? This one, I have to look at the degrees again. So like here, the degree up top is a 1. The degree underneath is a 2. If the denominator is bigger, then it's horizontal, and it's y equals 0 automatically. When the denominator is bigger, y equals 0. I don't even have to do any math. That one is all memorization, okay? And then the last one here, I look at the degree of the numerator is a 2. The degree of the denominator is a 1. So here the numerator is bigger. That's the oblique asymptote. So now I have to do some synthetic division. So when I do synthetic division with this, I put the 4 in the box. Remember, opposite of that guy. I write down my coefficients. It's been a while, right? I bring this guy down, I multiply, and I add straight down. And then I multiply, and I add straight down. And this interprets as x plus 3 with a remainder of 6. So that goes over the thing I was dividing by. And so what I do here is I'm looking for y equals mx plus b. So if I said y equals, this looks like y equals mx plus b, but then plus some fraction, I just go, oh, I only want the y equals mx plus b part. So I just get rid of that fraction. And again, the reason for that is something that's a little bit over your heads at this point. Okay, the reason for that is because of limits. And if I look at the limit as x approaches infinity there, that whole fraction becomes a 0. All right, so keep that in mind. So we end up with just the y equals x plus 3. That's it. So again, finding these is easy. It's just a matter of memorization. When the degrees are the same, divide the leading coefficient, y equals. When the denominator is bigger, y equals 0. When the numerator is bigger, synthetic division, find the y equals mx plus b. Okay?